In this lecture, we're going to be continuing our look at routing algorithms and looking at the distance vector routing algorithm. Distance vector is built around this equation, which looks a little bit intimidating, but it makes a lot of sense. Let's talk about this notation just a bit. D sub x of y is the cost of the least cost path from x to y. So we can think about x as the source and y as the destination. And d is the least cost, the distance. What we're saying here is that the least cost path from x to y is the minimum of the cost from x to v plus the least cost path from v to y of all the possible v's that exist in the network. So all of the neighbors v of x, if we were to compute this, whichever one is smaller, whichever neighbor has the least cost path from x. So by repeatedly applying this formula, we're going to be able to find the best paths in a network by only exchanging information among neighbors instead of having to exchange it among everyone. Let's work with this notation a little bit more. The least cost path from v to z is 5, which is 2 plus 1 plus 2, this route. From x to z would be, what, 1 plus 2? There's no better way of doing it than that. So that would be 3. And from w to z is 5 or 3 or 6. So 3 is our best for that too, through y. For these three neighbors of u, which is v, w, and x, these are the best cost paths of those neighbors. All right, so we're assuming some information that the algorithm wouldn't have, which is we could figure out what the best cost path is for these neighbors. What we want to compute is, given these three pieces of information, which is the d values for our three neighbors, what is the least cost path from u to z? That is d sub u of z. Does that make sense? The question we're asking? We're trying to find the least cost path from u to z, and we know the cost of the least cost path from each of our three neighbors, right? Our three one-hop neighbors. That's what we just figured out here, 5, 3, and 3. So the Bellman-Ford equation says that this least cost path du of z is whatever is smaller, the cost to get from u to v plus the dv of z. Maybe let's substitute some numbers in there. Okay, so that first cost, what's the cost u comma v? This is 2 because that's what this is. And what is dv of z? We just said it's 5. So 2 plus 5 is 7. All right, next line. The cost from u to x is 1, and the cost from x, the least cost path from x to z is 3. We found that up here. So that's 1 plus 3. And finally, the CUW is 5, and the least cost path from W to Z is also 3. So that's 5 plus 3. So if we sum all that up, we see that the minimum of those is the 4. So that tells us that the least cost path from U to Z is through X. That makes sense? Now, really, this U doesn't know the rest of the path. He just knows that X has the best path because X can get to Z in 3. So keep in mind that even though we can see the whole graph here, the algorithm, the distance vector algorithm doesn't. It just sees what each node sees what its neighbors see. Which is not the complete path, but just how long is the cost through each particular node, each particular neighbor. Perhaps we should have started from this as another Summary of our notation. This is our estimate of the least cost from X to Y. This is going to be our part of the distance vector. This is the cost, a node cost to a neighbor, X and V, where X and V are neighbors. And each node is going to maintain its own distance vector, which is a vector is a collection of values, right? And these values are the distances to all of the nodes in the network, right? An estimate of the least cost path to every node in the network. So that's really a collection of these. The node also maintains a set of distance vectors for each of its one-hop neighbors. That's V. So each node knows its distance vector, and it's going to exchange that with all of its neighbors so that it has its own distance vector and a distance vector of each of its neighbors. And by updating, it can update its distance vector to compute a routing table based on what it overhears from its neighbors and the cost to each of those neighbors. Okay, we're going to look at an example of this in just a moment. So a very broad overview of the distance vector algorithm is we're going to send our distance vector to our neighbors and receive distance vectors from them, and then update our distance vector using the Bellman-Ford equation, which we just walked through, where we're finding the minimum cost plus distance for each of those one-hop neighbors for each particular link, each particular node. And then we're going to repeat this process over and over again. And if things don't change in the network, this will converge. It will converge to the actual least cost path to each of those nodes. If a distance vector to any destination changes, then we have to notify our neighbors so that they can update their distance vectors. These are three important characteristics of the distance vector algorithm. It's iterative. That means it repeats until no more information is exchanged between neighbors. We're just going to keep repeating and sharing this information. It's asynchronous. It doesn't require all nodes to operate in a synchronized kind of lockstep synchronization fashion. And it's very distributed. Each node acts independently based on the information that it receives from its own neighbors, that is, its direct neighbors, and then it distributes the results back to its own neighbors. So there's no broadcasting. There's no centralization at all. It's very distributed. Okay. So the first thing we're going to do is we're going to look at a new network. We're going to figure out what the distance vectors are at each of the nodes in the network. And then we're going to go through one iteration of this algorithm to compute least cost paths globally. Remember, this is my little sentence summary of distance vector. We're telling our neighbors about the world. All right, so we're telling our neighbors, we only have communication with our neighbors, but what we send each of our neighbors is our view of the world. That is our view of the complete topology and the least cost paths in that. All right, so let's look at this. We're going to pretend like we are A. At A, he has a distance vector that looks something like this. Let's go through each of this. A knows that it can get to A in 0, because that's itself. Okay? A can get to B in 2. A can get to C in 4. A can get to D in 10. A can get to E in infinity. Right? So initially, if there's no direct connection, infinity is our cost. That's our distance. And we put these distances together into a vector. Does this make sense how we compose the distance vector? Questions on this? All right, so as long as everybody knows their one-hop neighbor information, they can create one of these. Well, let's go through and compute distance vectors at each of the 5 nodes in this network. At B, it has this, right? B is connected to everybody. It's 2 to A, 0 to B, 1 to C, 6 to D, and 9 to E. Notice this distance vector, this initial one, is just the actual cost. That's C with 2 nodes, right? The cost. And we can assume that that's a good starting point for our least cost path, our D value. At C, it looks like this. We got 4 to A, 1 to B, 0 to C, 4 to D, infinity to E because it's not directly connected. D looks like this. D is 10 to A, 6 to B, 4 to C, 0 to D, 2 to E. Yeah, this is its distance vector. And E is infinity to A because it's not connected. It is 9 to B, infinity to C because they're not directly connected, 2 to D, and 0 to E. Each node, by knowing local information, can create a distance vector that's going to look like this. Right? It's the cost of that node going directly to that node, and if it's not directly connected, it's infinity, and the cost to itself is 0. All right, this is our setup. Now we're going to start sending those distance vectors to our neighbors so that they can update their routing table. Are you ready for this? You don't look nearly excited enough. For the rest of this example, we are going to be at A. We're going to be A. Okay? Now, keep in mind that everybody else, all the other nodes besides A, are actually doing the same thing, the same process, and updating their numbers appropriately. But for the rest of this example, we're just going to be A. All right, so A is going to receive a distance vector from B and C, and also D actually, but it's not shown. Right? We're going to get a distance vector from B and C. When it gets those distance vectors from its neighbors, A is going to look through here and compute an updated least cost value using the Bellman-Ford equation. And it will also remember which neighbor had that least cost path. What we're doing here is trying to create this new routing table. How do we get to A, and what node should we go through? Well, we know we can get to ourselves in 0, and we go through ourselves. That kind of doesn't apply. All right, so our first real question is what goes in this column, which is how do we get to B? Well, I can get to B through B at a cost of 0 from B plus the cost to get to B, which is 2. I'm using delay instead of cost. We probably should say cost. So that's, I can get to B through B in 2. Let me show you. So it's the minimum of 0 plus 2, yeah, the 0 coming from here and the 2 coming from here. Or I can get to B through C, right? And to do that, I can get from B to C in 1 and from A to B in 4. So that would be, or I can get to B through C in 5. I know that C can get to B in 1 and A can get to C in 4. So that's 5. Our two options of getting to B are through B at a cost of 2 or through C at a cost of 5. Which one do you want to choose? All right, the smaller one, the 2. So that means we're going to say I can get to B through B in 2. The next piece, the cost from A to C. Really, this is not the cost, but it's the least cost, the D value. All right, so I can get to C through B at a cost of B's cost, which is 1, plus B's delay, which is 2. So that's 1 plus 2, 3. I can also get to C through C at a cost of 0 plus 4. Yeah? Which one of those is smaller? The 1 plus 2. And now we've actually discovered some new information, right? We've just found that it's faster to get to C through B than to go directly to it. So now we've updated our routing table to reflect that. So if you need to get to B, you go through B. If you need to get to C, you go through B. Make sense? There is a mistake in this that I just realized, which is we should also have another row here, which is from D, because D is a one-hop neighbor of A. And we would also need to look at that and see its values and see if it's a more minimum value. We can see through here that it's not, right? That 10 is so big, it's going to be worse than anything else that we could do to get to B and C. But we really should consider it, and distance vector would. Okay, so let's keep going. Let's consider this fourth column. How do we get from, what's the least cost path from A to D? Well, we can get to it through B at a cost of 6 plus 2, where 6 is the least cost path from B plus the cost to get to B, right? 6 and 2, 8. Or we can get to it through C, which at a cost of 4 plus 4. They both happen to be 8, so we could choose either one. They're the same cost. We could just randomly choose one. Yeah. Just to mix it up and give C, some traffic. Huh? And lastly, can we get to E now? Well, what are our options? We can get to E through B at a cost of 9 plus 2, 11, which is, right, we've got the 9 here, and we know that we can get to B in 2, or we can get to E at a cost of infinity plus 4. Which one of those is smaller? Yeah, right. Always choose the one that doesn't include infinity. Yes, Camille?
Going to D, would you not go BCD?
B, C, D to get to...
To get to D from A. Because that's 7.
That is better, but we haven't discovered that route yet. With that, we need to iterate. So we found a route, but it's not necessarily the best. We haven't converged on the actual least cost path and for more iterations. But that's a really good question. Because what you see from this is, we find here that we can get to E in 11 through B, but that's not the best path. We found this last time, right? The best is 2, 1, 4, 2, right? That's 2, 4, 8, 9. So 9 is the best. But at least we found, even after one iteration, now we at least could get to E in 11. So this is, right now, I've created this new routing table based on this information by comparing all of the other distance vectors that I received. And like I said, I did forget to put in the distance vector from D. So think of this as a highly simplified example. This is after one iteration. What do we do next? Rinse and repeat. Right? We just keep going through this process where we get a new distance vector, and then on the next cycle, we will send out our new distance vector to our neighbors, and likewise they'll send it to us, and we update everything accordingly. And the beauty of the math is, the beauty of this algorithm is that if the values aren't changing, that is, the actual link costs aren't changing, then this algorithm, distance vector, converges to the actual least cost paths. So I think this is very elegant. It's nice that it's so distributed, that you only have local information being exchanged. Over time, the information will spread through the network and the best paths will be found. And this is distance vector. What questions do you have about distance vector? I know you disliked it when you read it in the book. Yeah, I think the formulas make it more intimidating than it actually is. It really makes sense if you think, okay, well, that guy can get to it in this far, and if I know it takes this long to get to him, so whichever one of those sums is the smallest is where I need to go. Now, let's do a little comparison to sum this up, and then we'll talk about some more slippery issues with routing protocols. So link state, remember, is telling the world about your neighbors. You're broadcasting your link state information to everybody. Distance vector is telling your neighbors about your view of the world. Right? That you're telling them about, this is what I think is the overall least cost path to everybody in the network. In terms of messages, there's more messages because they're broadcast in link state, fewer with distance vector because they're just exchanged. The message size would probably, though, will be smaller with link state because you just have to send your links, whereas with distance vector, you have to send the entire distance vector from you to all the other people. Right? Your whole distance vector is as big as the number of nodes in your network. The conversion speed, link state is faster because as long as it knows the whole topology, you can run that algorithm on one node pretty quickly. Right? It's just computation. It doesn't take communication to figure it out, and it knows the least cost paths. Whereas conversions take some time in distance vector because you don't have all the information initially. It takes several iterations to learn everything. In terms of robustness, though, link state is better. That is, it's better at adapting to change. Distance vector is worse. Link state protocols are generally more scalable than distance vector, and so you may see them used more often in the broad internet. We'll talk more about specific routing algorithms in the next section, 4.6. On the next two slides, we're going to talk a little bit about why and how distance vector is bad at adapting to change. So if the link cost changed, or if this 4 goes to a 1, this is the books example, we need to detect that change and then update our routing information. We then have to send that out to our neighbors, right, so that they know about this new, better path. That is, the distance vectors will be recalculated, and our neighbors need to know about this new distance vector that we just computed. The end result of this is that good news, so if link costs go down, that good news travels fast, and that new route will be taken advantage of. Unfortunately, bad news travels slowly, and they call this the count to infinity problem. The book explains this, I think. Perhaps you don't think it's very well, but they got kind of through the painful details of how you end up going through these this instability where there are 44 iterations in this example before the nodes learn about this actual change. This is basically a result of the fact that when you send out information, that is, when you share your distance vector with your neighbor, he doesn't know that what the complete route is. You're just advertising a whole cost. When the values change in this way, the convergence, you kind of end up accidentally lying about it, where one guy thinks, hey, that's a better route, I'll go through you. Oh, you also used that link that just changed. And therefore you're just as slow, but somebody in an intermediate hop had lied about the actual value. We'll look at an example in the book to try to firm that up. But basically, you can do a lot more damage to routes in distance vector because what you're communicating to all the other routers is not, hey, this is information I know firsthand, but this is information I've inferred from further away. You see? So it's like, hey, I might have bad information and all of a sudden be advertising that this route costs this much because I think it does, but somebody closer to it actually knows that that link has gone down and therefore is not a good path. But I don't know what they know yet. All right, let's sum up this comparison stuff. We looked at this a little bit, but number of messages, we said link state is more, distance vector is less, and you can kind of look at how I estimated the complexity of that in terms of the number. The message size, we already hit on this. Link state is smaller, distance vector is larger, but we have to send more messages. In terms of complexity, link state is n squared or possibly n log n, whereas distance vector would be faster because you just have to compare something on the order of the number of nodes, which is a whole distance vector. Convergence speed, link state is faster, distance vector is slower because of that iterative property. Loops are possible, and you got that count to infinity problem. Bad news travels fast. And in terms of robustness, this is what I was trying to say before but didn't say very well. Link state is more robust because nodes can advertise an incorrect link cost, but in distance vector you can advertise an incorrect path cost. So you're giving even broader bad information. So it means you can have a much worse effect if your information is bad. The book mentions that in 1997, a malfunctioning router at a small ISP gave national backbone routers bad routing information, and this caused the other routers to flood the malfunctioning router with traffic and caused a large portion of the internet to become disconnected for several hours. So it's kind of, you can imagine, you could do this maliciously or accidentally. If you're a router, right, and you say, hey, I can get anywhere you want to go in 1, right, and, which is 1's really low, let's imagine, in our fake numbers that we're making up. Then everybody's like, hey, he's got awesome routes. Let's send everything to him because his routes are awesome. Whereas you just take all that traffic and drop it, right? You've created like this black hole, right? You see the danger, right? If you trust everybody, you're going to take advantage of whatever the minimum route is. And apparently this was a malfunctioning router that had bad information, and it caused the internet to go down. This was in 97, so that's a long time ago. You can see how important it is then for routers to have authenticated exchanges with each other, because you can't just trust anybody if this information is too important to not be true, to not be authentic. So that's the way I'm sure that problem is handled now. But security issues are ever present, and we need to be thinking about that at every level of the network. All right, so security is important. Distance vector is not that bad to understand. Link state is cool. Dijkstra is cool. Maybe we kind of prefer that, even though it does require that global exchange of information. So come back next time, and we'll talk about how routing actually works in the real internet.